morning, guys. Today we will be talking about this next topic, PCM receiver. Now, whenever we are talking about the PCM system, pulse code modulation system, this pulse code modulation system is basically analog to digital conversion system, where we use the digital signal to actually get the better results and better optimization of our resources. Now, what we are having is, we have already talked about the PCM generation. PCM generation, or we can say the PCM transmitter circuit, is a very complex circuit where we are using the quantization technique, we are using sample and hold technique to actually generate a proper amount of digital signal so that we can recover the same signal. At the same time, whenever we are talking about a PCM system, that system has one problem. There is always ambiguity and the question of choosing the quantization level, number of quantization level, because there will always be a quantization error, and that quantization error cannot be eliminated completely. Now what we can do? We can actually minimize that quantization error, but not actually reduce completely. Now, why is it so? Because if we are increasing the number of quantization level, the bandwidth of the signal will be increased, and that continuous changing in bandwidth and that problem will actually occur in this PCM system. Now, what is happening is, whenever we have a PCM signal at the receiver side, what we have is this PCM signal will be regenerated. Now this regenerated will always be synced with the signal, and that signal, for that purpose we are using a timer circuit. Now this timer circuit will actually help us to determine which quantization levels are available to us. Now with this circuit, this timer circuit, this time pulse will be provided. Right now, whenever we are talking about the time pulse, that is the clock pulse. Now this clock pulse will be provided to regenerator, SP converter, that is, whenever we are talking about the SP converter, that is serial to parallel converter. As we know, initially we have converted it to parallel to serial converter in PCM generation, and to sample and hold circuit. As we know that sample and hold circuit, or the sampling circuit, is the circuit where we actually get the sample signal and how much sample signal was generated, and what are the sample duration. It will be decided by this timer circuit. Now, first of all, whenever we have this PCM signal, it needs to be regenerated. This PCM regenerator will generate the actual PCM signal which was originated in the last circuit, because initially whenever we are getting this PCM signal, it will be comprised with noise part. So noise part will be there, though it is a very lesser noise, but noise part will be there. And so what we need to do is, we need to generate the actual PCM signal without that noise. Now that noise is because of the channel we are using. That can be wireless channel or the wired channel. So due to different circuits, due to different methodologies, that particular signal or that particular noise part will be different. Now this PCM signal needs to be sent to SNP converter, serial to parallel converter. As we know, this serial the signal which we are right now receiving is in serial mode. So we need to generate in quants mode or V-digit mode. Now that V-digit modes can be generated by SNP converter. Initially we use the different circuit. Now we are using to just change it, because right now what we want to do is, we want to convert this particular signal. This signal is PCM, but this is not a proper digital signal. There are some added parts too. So this will actually make us a proper V-digit signal, so that this digital signal, proper digital signal, can be converted into analog signal. Now this can be happened by D2A converter, that is digital to analog converter. This digital to analog converter will change this signal into analog signal, which was actually the modulating signal, and we will use it to get the SHN circuit and the proper signal which was earlier available to us. Now why we are doing this S and H circuit? Because we took a particular signal and sampled it at different levels. At different time and different levels we sample it. Those sample needs to be distinguished. Where are those samples and how much pulse is there at that point of time? What is the amplitude over there? So that amplitude and that information needs to be understood, and that circuit, that particular signal needs to be generated. After this we will pass it through LPF, that is a low pass filter. Low pass filter will actually cut off the frequency above that particular signal, and the only particular band will be there where we actually want to have that signal, because even in this process we are actually modulating the signal, and that modulating frequency is on the higher side. You will get the signal YT or the modulating signal at the outside part of that LPF, low pass filter. What is telling us the whole sequence of these particular circuit? Now whenever we are talking about this circuit, we can see that it is not exactly the same modulating signal, but somehow it is more or less related to it. I told you earlier that yes, we have to choose what is the best optimization level and what is the best quantization level to eliminate that particular quantization error. Let me remind you again, we cannot eliminate the quantization error completely in this circuit. So this is what we are getting. Now this is the signal we are getting, SQT after sample and hold circuit, and these are the quantization level. And look, you can see that actual signal is actually on the left side or in the right side of that particular signal. So this is how it was generated. Yes, there are some quantization error, but yes, you have already got the best out of resources. So this is how you are going to generate a same modulating signal through this PCM receiver circuit. I will give you time to see this circuit and to note down all the important parts and their workings. Thank you guys. Now we will be talking about the quantization error. As we know that quantization error is the most important part in this PCM circuit, and this quantization error will happen again and again, and what we need to do is we need to minimize it to its optimum level, where we get the better signal to noise ratio. The noise is at the minimum side and signal is at maximum side. Now how can we calculate that quantization error? It can be calculated by two bases. If suppose quantization happened uniformly, there are uniform Q quantization levels available to us, so there is a possibility that we can have this quantization error be calculated and be minimized. Now as we know, in the last part we have already gone through it, and in the transmission side we have already calculated this quantization error. This quantization error is the signal after quantization minus the original signal which is available there. Now this NTS, whenever we are talking about NTS, this is a digital signal. So digital signal will be there. We can actually have the reference signal by which we can actually calculate the quantization error. Now what will happen is, let us suppose this particular signal is actually propagating, and this particular signal is going through a process, that is quantization. Now that is, suppose it is a uniform quantization. Now it is a uniform quantization, so we can understand that there will be a limit to it. So suppose what will be the maximum limit of that particular quantization levels. So suppose if there are numbers of levels have been defined, so quantization levels will be defined Emax equals to delta by 2, and suppose initially there is no error or there is no quantization happened, so delta by 2 minus 0, that is the E maximum part, and that can be understood as E maximum equals to delta by 2. So that is the maximum level. So suppose if you are talking about this one, this term, so it is showing that it is floating between minus delta by 2 to plus delta by 2. Now this is the uniformly distributed random variable signal. Now whenever we have this uniform distributed random variable signal, we can actually understand, or we can understand its characteristics by this equation. So what will be the total amplitude range of this particular signal? Now how it will float? Now suppose this is the signal, fxx is there, and if it is this value delta is very small. If delta is really very small, then the possibility is that this particular variation will not happen very frequently, and this changes will be uniformly distributed. Now if those signals are uniformly distributed, so what will happen is, if you are actually drawing the curve and simply putting the equation over there, so this is the maximum limit of that particular equation for both when the value x's value is less than or equals to a, or x's value is greater than equals to b, or two ranges where it is floating around. So if there are two ranges available to us, and if it is floating around then, so it can be understood that fxs is 1 upon b minus a unless it is 0 at this point and at this point. Both are zeros, and at this point we will get the maximum value, that is 1 upon b minus a. Just take this example and let us draw its form. If you are talking about this signal, so it will be equally distributed around two parts, plus del by 2 and minus del by 2. It will be distributed around both the parts, and the maximum limit of this one is, and if it is, suppose this, if you are talking about this error, now this error is this one, and if you are talking about this one, 1 upon delta equals to 1 upon delta by 2 minus delta by 2. Just think about this one. So delta in normal, delta equals to 2 upon q. At q are the quantization levels we have been doing, number of quantization level which have been done in particular signal. Now this is happening over there. So to calculate this one, so if you are talking about this signal, so how we are going to draw it? E equals to 0 when error is less than equals to delta by 2. It is 1 upon delta when it is between minus del by 2 and del by 2, and again 0 when it is greater than del by 2. You can see it over here. This value is 0, and here is the maximum value where we are getting it, and that is 1 upon delta over here. Now we will talk about the SN ratio of this particular PCM signal. So how we are going to calculate an SN ratio? We already know about the quantization level. I will give you a second to just see it. So what are the equations and how we are going to understand those equations? Now in this particular system, we can see that we have already understood the function of this particular system and maximum quantization error in this particular system. Now this maximum quantization error is kept as minimum. This is the minimum size where we have to choose what is the best for us. Now we are calculating this SN ratio, signal to noise ratio. Whenever we have this signal. So there will be a noise part and there will be a signal part. So how much is this? So whenever we are talking about SN ratio is signal power upon noise power. That is how we are going to calculate it. Now if you are talking about noise power and signal power, what will be the? Now as we know that voice power is N equals to V square by R, resistance in that particular circuit, and the voltage of the circuit, V square R, or we can express it as I square R. Here I is the noise part. We can take both the parts. Now if we are talking about the V square, it is the normal mean square value of that particular signal. So in this system, E square equals to E square bar equals to V square noise. Now this X square equals to X square equals to. Now if we are talking about this equation, it is the linear function or uniform distributed function. So it can be expressed as x square fx dx. Just put the value over there and you will get it. Minus del by 2 plus del by 2, this is the range over which we are working. E square is there and 1 upon delta dE. Just put it over there and solving it, simplifying it. This what we are getting is 1 upon 3 delta q by 8 plus delta q by 8, or E square equals to just putting the value over there. Yes, solve it from this equation. Now what is happening is this noise part will be V square noise divided by R. That is the root mean square value of this voltage. Now if you are talking about the quantization error part, if you are talking about as error part, so this will be the mean of all the errors, and that will be equal to V square, all the noises available to it and the voltage available to it. So at x square, that is the mean square value, will be the Ex square, and that will be plot around minus infinity to infinity x square dx fx dx. This is the normal function that we have where we have to calculate it. Now if you wanted to calculate the quantization error part, that part actually the limit is minus del by 2 to del by 2, because we are already understand that it falls in between two values over there, here and here, minus del by 2 to del by 2. two values are provided over there. So in between that it will work. Again you put the value over there. So this will come as del q by 8 plus del q by 8 and 1 by 3 delta. Just solve the equation and you will get this part. So E square, root mean square of this value is del square divided by 12. Now this value we will put it in SN ratio. You already got the value. Now we will put the value over there. How we are going to put that value over there? Now just putting the value over there. So V square noise equals to del square divided by 12. Now just talk about normalized value of this one. So for a linear quantization, we can say that this is the noise level in any kind of system. Now just put the value over there. If you are talking about this value to get the SN ratio in that system, we have already calculated the noise part, so we can calculate the signal to quantization noise error for linear quantization error. Now if you are talking about this one, S divided by del squared by 12, that is the value. Now number of quantization level Q equals to 2 to the power V. Here V are the digits. We have already done this. V are the number of digits available in that PCM circuit and Q are the number of quantization level. It will be 2 to the power V. Now whenever we are talking about this one, and the maximum amplitude range in this particular circuit is 2x maximum. So delta equals to 2x maximum divided by V. 2x maximum, this is the maximum value limit if x is floating around there. So just put the value over there, upon Q, if you are putting the value over there, and it will be 2x maximum divided by 2 to the power V. So this will be the value of delta. Now we get the value of delta. So what will be the value of Sn in this particular circuit? Sn equals to P upon this 2x max upon 2 to the power V square into 1 by 12. We are putting the value of delta over here, and what we are getting is 3p upon x max square into 2 to the power 2v. So Sn ratio in this system and if we suppose x max is 1, then it is 3p into 2 to the power 2v, and just calculate this one. Now this is, as we know, this is a normalized signal. In this particular equation, P is the power. Now if this is a normalized equation, the P will be less than equals to 1 if it is a normalized and linear function. Just see this. What we have done is we have calculated this value del square upon 12. That was the noise power. Now this noise power, if you want to put it to calculate the signal to noise ratio, what we have to do is we need to put signal power divided by this noise power, that is 12 square delta square divided by 12. Now there are number of quantization level available to us are 2 to the power V. V are the number of digits available to us. Now maximum amplitude range of this particular signal will be 2x max. Now delta will be calculated at 2x max divided by Q. 2x max divided by 2 to the power V, that will be the delta. Just put the value over there. This P is the power, signal power divided by 2x maximum upon 2V, 2 to the power V squared into 1 by 12. Just put it over there, and what you will get is 3P divided by x square, x max square into 2 to the power 2V. Now whenever we just put the value over there, and the value will be 3P into 2 to the power 2V. Now it is a normal function, normalized function, so P will become as less than equals to 1. Just suppose it is 1, so Sn will be 3 into 2 to the power 2V. That is the value. Now just putting the value over there, and we will talk about the range of this particular equation. Now in the last equation, what we are getting is signal to noise ratio Sn will come as less than equals to 3 into 2 to the power 2V. Now if you are talking Sn ratio, that will be calculated in dB, decibel level. So just putting the value over there, 10 log 10 Sn is less than equals to 10 log 10 3 into 2 to the power 2V, and Sn dB will be less than equal to 4.8 plus 6V dB. So this is the value we are getting from the above equation. We have just solved it. 10 log 10 3 plus, again if you want to solve it, it is very simple method. 2V will be there, and into 2V log 2 10 log 10 2. So just putting the value over there, you will get this equation. So this equation, by this equation we can have this value. So what will be the Sn ratio of this particular signal, PCM signal, when quantization level happens, and we have given the value of V. Thank you guys.